Hello, welcome to this video relating to the characteristics of distributions, dot plots and stem plots. Yes, I know. My name's Darren from Maths Guru. Really good to see you. If you can, subscribe to my YouTube channel. Just lets me know that you're watching and is greatly appreciated. Or follow me on all the other social media stuff. TikTok, I'm just on there. Very exciting. All right, so what are we doing today? Well, let's get into this. Our learning objectives is to be able to identify the key characteristics of a data distribution. What on earth do I mean by key characteristics? Well, it's coming up. Don't rush me. Be able to construct a dot plot and a stem plot for numerical data. All right, so it's really important. Previous videos we looked at categorical data. Now we're going to look at numerical data, and it's so important that you know how to choose the right graph or diagram for the right set of data. Okay, so as I say, we've been looking at building up our understanding of how we describe and display categorical and numerical data, how we can classify them as numerical or categorical and subclassify too, as well as being able to sort of interpret frequency tables and bar charts and display and describe numerical data. All right, so we've done that. Now let's get on with the exciting stuff. When you look at data, particularly on graphs, you are looking for things about the shape and the center and the spread of the data, all really, really important. So that's the stuff that's going to go in your summary book. The first thing we look at is the shape of the data. Now, imagining I've taken a load of numerical data and I've put it into a graph, all right, or I put it into, in this situation, a histogram. How do we know that's a histogram, by the way? Because there's no gaps. Yay! And we're also dealing with numerical data. Numerical data, always a histogram. Now, what we notice here is this data seems very, very pretty, all right? It seems, well, symmetrical. There's no other word you can use for it, really. It's symmetrical. That one there is perfectly symmetrically, in fact. How do I know that? Well, we've got 3 bars to the left. We've got 3 bars to the right. What have I got here? I've got 1 bar in the center. Each of the bars on either side of that seem to be exactly the same height as each other. That couldn't be more perfectly symmetrical if it tried. Right? So a symmetry means that when you put a line down the center of it, the left and the right look roughly the same. Now, obviously, when I look at histogram B, you're going to turn and say, well, that's not symmetrical. Well, it's not perfectly symmetrical, but actually, sort of ignoring the fact that these 2 bars here are a little bit shorter, it does seem that the data is centered around that middle bit. It does seem that it's sort of symmetrical. It's not too far one side or the other. And in that situation, we would describe it as approximately symmetric. Right? It has an approximately symmetric form. Now, I've not really known any data in real world to come out as perfectly symmetrical. So a hint for what you're going to come up against later on, just don't describe things as symmetric, describe them as approximately symmetric. Right? That word approximately is really, really important. Now, once we've done that, if it's not symmetric, then it's got to be leaning one way or another. And in this situation, what we can notice here is if I was to draw my sort of line over it, and I tend to do this just to help me, I notice that the data seems to be pushed more to the left than, he says doing it the wrong way for the camera, more to the left than it does to the right. Yes? And in that situation, as you can see from the diagram here, it is then called positively skewed. Very exciting, positively skewed. Now, I always get these wrong, personally. That's why I have them in a summary book. I can guarantee in a week's time, if you asked me what that was, I wouldn't know if it didn't have positively skewed on. My brain just cannot remember this stuff. That's why I would put it in my summary book. And obviously, if the data is actually pushed all the way to the right in that situation there, then we would say it was negatively skewed. And that was the first question this year on the VCEE Year 12 General Maths exam. I actually gave you a graph and just said, describe it. Whew, did that cause a lot of problems, right? So we're looking for a lean, we're looking for a symmetrical. That's one way, the shape of the data. What else? The center of the data. Where do we think the center is of this data? Where's the middle data item? Now, again, please remember these are just numbers, right? So a histogram is just showing you that, for example, here, there are a certain number of 5s. There are a certain number of 6s. There are a certain number of 7s and 8s and 9s and 10s. So a histogram is just showing you a different way of interpreting the data. But if we were to put all of these in an order, we would have just loads and loads of numbers in a list. Could we find that middle number? Yes, we could use whatever methods we had previously to find that middle number. But the chances are this data is going to have a center somewhere around there. Now I don't know for a fact because I don't have the frequencies of those bars, but the chances are, all right, the chances are that if I added the heights of all of these 4 bars here and added the heights of all those 4 bars there, they'd be roughly the same. The center would be somewhere there. Where do we reckon the center would be here? Possibly over here. So what we notice here is the center would be around 7 for histogram E, and the data here would be roughly around 12. Well, what does that matter? Well, because we've got 2 histograms, we can compare. So it may well be in a test out of 15, right? So I did a maths test with one group and I did another maths test with another group. Well, we could now tell that the people in histogram E didn't understand a word of what I was saying, or they really struggled because their sort of central score was about 7. But histogram F, my other group there, obviously understood a lot better the test I was doing or the work that I was doing and got a higher score, roughly centered around 12. Right? So we use the idea of centers all the time in maths. Then we look at the spread of the data. Now we've got to be very careful about spread because we can do it in 2 ways. There's the range, that's the one you've been using all the way through school, and the interquartile range, which you may have met before. The problem with the range, and there's a big problem with the range, is that actually it can be really messed up, and I'm going to come back to that later. But let's just take at the moment that the spread of the data is how wide the data fits, from the biggest number to the smallest number. And in this situation here, what do we notice? Well, we've got our data going from, what would that be, 0, 1, 2, 3. So let's say 3 to 10. So our data there, so my scores for that particular group went all the way from 3 to 10. So we would say there that the range or the spread of the data would be about 7. That means they're fairly closely packed. They're not very variable. We like that word, variability, really important. What about this one here? Well, what we notice is the lowest number there was 1. The highest number there was, let's say, 14. So my range in that situation would be 13 points. Right? So there I've got students spread out all the way. High score of 14, lowest score of 1. Which would be best? Would I want my groups spread thinly or widely? Well, generally speaking, depending on the context, we want it to be narrower. It means that they're more centered, that they're more squashed together, that there's less variability. We don't want a lot of variability. Now we're going to move on to dot plots, which is plots with dots. And I think we've met these before, but again, a dot plot is awesome because it gives us so much information. So if I look here, I can see, for example, that I've obviously gone out and done some sort of a survey, and I've asked people, how many hours did you work this week or today? And can I work out how many people I asked? Yep, I can count the dots. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I asked 10 people, and I worked out that, one person worked 4 hours, 2 people worked 5 hours, 3 people worked 4 hours, and so we go on. So it's great here. I can see the range of my data. Right? My lowest data item is 4. My highest data item there is 7, so I know that my range would be, 7. Highest data item is 9, so I'd say 9 minus 4 would give me 5, all right? So I can see that the range of my data is 5. Is it skewed? No, all right? Again, if I was to draw this, I would say it is approximately symmetrical. Why? Because I'm obviously centered around 6. I've got 3 data items on this side, 3 data items on that side. Now, again, it's a little bit subjective. Why? Because there's not a lot of data in there. Right? So talking about the shape of this is a bit more complicated. But, all right, dot plots we love. Now, again, lots of people lose huge numbers of marks when they're being asked to construct a dot plot. Why? Because they don't use a pencil, they don't use a ruler, and they don't use the proper scale, all right? So you will lose marks in year 12 if you don't use a pencil, if you don't use a ruler, and you don't use the proper scale. And you have to be accurate. I'm going to say that in the next video. So let's construct my dot plot. The number of hours worked by each of 10 students in a part-time job is as follows. Construct a dot plot. Now again, I don't have a ruler, and PowerPoint isn't very good at allowing me to draw straight lines. So let's assume that is straight. And what is my smallest value? We're going to try and find my smallest value, which seems to be 4. So 4. What's my highest value there? It seems to be 9. So there's 9, 4, 5, 6, 7, 8, 9. Now again, what's the problem with that? My gaps aren't equal, so I probably should have left the 9 till a little bit later on, but we'll go with it for a moment. 4, 5, 6, 7, 8. And what are we going to do now? I'm just going to do my dots. 6, do a dot, cross it through. 9, do a dot, cross it through. 5, do a dot, cross it through. 8, do a dot, cross it through. 6, do a dot. 4. Now you'll notice I'm crossing them through each time so that I don't make a mistake, I don't miss a data item, and I don't get anything wrong. It's such a small thing to cross them off, but it makes a huge difference, right? And there we go. There is the dot plot of my data. But don't forget, I would have to write under here, hours worked, so that I told my examiner or whoever's marking this what the data actually stands for. Ooh, then we get to stem plots. I love stem plots, right? But again, word-wise, I can't explain them. I just have to give you an example of how to do them. Now, a stem plot has basically two sections. There is a vertical line. On the left, we have the stem, and on the right, we have the leaves. And now, in this situation, what I'm going to do is I'm going to look for my smallest value. Now, my smallest value here appears to be the number 2. What is my largest value? I'm going to write that down here. My smallest value is 2. What's my largest value? 45. Can I get any help for 60? All right, so my largest value at the moment appears to be 60. So I want to go all the way from 2 to 60. Now what I'm going to do is I'm going to go 0, 1, 2, 3, 4, 5, and 6. Now basically that 0 stands for all the single digit numbers. So 1, 2, 3, 4, 5, 6, 7, 8, and 9. This 1, I'll show you, stands for all the numbers from 10 to 19, the 2 from 20 to 29, and so on. So here we go. First number is 15. So I'm going to go to the 1, and I'm going to place a 5 there. That number now stands for 15. 2, I'm going to put a 2 here. 24, I'm going to put a 4 here, all right? Because 2 and the 4 goes 24. 30, 3 and a 0. 25, I'm going to put a 5 there. 19, I'm going to put a 9 there. Now what you'll start to notice is as I put more numbers into the rows, I'm lining the columns up. That becomes really important as well. 24, 33, 18, my eyesight's getting worse, 60, 42, 37, 28, 28 again, hope I don't run out of room, 17, 19, 52, 55, 27, 5, 7, 19, please don't let me run out of room, 45, 19, and 25. Woo. There we go. So there is my stem plot. Now that's actually called an unordered stem plot, and it's not actually finished. And the reason being is there is the most important part of a stem plot is in fact the key. Right? So I always have to write a key. Now when I do that, I choose one number from my table. So let's choose the number 15, and I would say 1 line 5 equals 15. Now the reason being is we can actually do decimal numbers in the same way. We can actually, if I had these numbers as 1.5, 0.2, 2.4, 3.0, we would actually look at exactly the same as this, but I would just have a different key. We'll come back to that in a moment. Now, the problem with this is that's called an unordered stem and leaf plot, right? We actually wanted to do an ordered one. How do you do an ordered one? Well, now having done the hard work with the unordered, I would redraw my diagram. Again, sorry for the space, 0, 1, 2, 3, 4, 5, and 6. And for each row, I'm actually just going to put the numbers in numerical order. Now, for this first row here, I know the numbers are already in order, 2, 5, and 7. This one here, are they in order? No, I would have 5 first, and then I would have the 7, 8, and 4 9s. 1, 2, 3, 4. This one here, 2 would be 4, 4, 5, 5, 788 037 25 25 and 0. Now again, we'd still have to copy the key down. All right, so 1 line 5 equals 15. Now why is this important to us? Well, when we want to do any sort of mean, median, mode or range for the data, we always have to make sure it is ordered. We have to make sure it's ordered. So now I can actually use this information to answer questions like, well, what's the range? What is the range? Well, the range would be the smallest value and the largest value subtracted from each other. Now, it's not 0 minus 0, all right? Because again, people make silly mistakes here. That 0 there stands for 60. So my range would be equal to 60 minus that 2, which is 0, 2, which is actually 2. So in that situation, my range would be 58. But the question says, comment on the shape of the distribution. What does it mean by shape? Well, the diagram's the wrong way around. Well, actually it isn't if I turn my head to the side, because I can actually draw this here. So the first question is it symmetrical? It's skewed, isn't it? It seems to be pushed to one side. Is it positive skew or is it negative skew? And again, if you're not sure why, turn your screen and have a look at it from the side. Makes life really, really useful. Well, again, can't remember. Let's go back. There we go. It looks like that positive skew. It's more to the left. And so in that situation, I would say that that was positively skewed. Now, as I say here, the important stuff for a stem and leaf diagram is that the numbers are in columns, right? So what I'm saying is that all of these numbers, when you put them there, are all in straight columns, right? You must show your key. That is seriously, seriously important. And you must use a straight line. Use a ruler, please, guys. All right, now again, it will help us find things like the mean, the median, the mode, the range, and the interquartile range. So in this situation, as I said, I know that the range is the biggest number, which we said was 60, minus the lowest number, which is 2, which is 58. What about the median? I want the middle number. Well, I suppose the first thing we need to do is say, well, how do I find the middle number? How many numbers are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. There are 25 numbers. So where would the middle number be? Well, there's lots of ways of doing this, but I can cross numbers off the start and the end. That certainly would help. So 1, 2, 3 off the start, 1, 2, 3 off the end, 1, 2, 3 off the start, 1, 2, 3 off the end, 1, 2, 3 off the start, 1, 2, 3 off the end, 1, 2 off the start, 1, 2 off the start, 1 off the start, sorry, and 1 off the end. And there we go. There is my middle number. My median is not 5, is it? Yes, it's not 5. All right, I don't know why that number there is a 9. That should be a 2. All right, but the number therefore would be a median, would be equal to 25. Right, and that wouldn't have been right. If I go back to my previous one and try and do it on my unordered step diagram, I get the wrong answer, which is why we have to order it. Okay, now which graph do I use and when? That's really important, isn't it? Because if you're in an exam and you've been given the data and they ask you to choose the most appropriate way, you've got to know, and here's a table from the Cambridge textbook. So, dot plot. So what they say here is used when there is a small data set, all right? Say, for example, n is less than 30, all right? For discrete data. Dot plot, you don't really want to put decimal numbers on the dot plot. So just use whole number values. How to do with a hand or technology. Actually, your CAS can do dot plots for you. Very exciting. Stem plot, small data set. Again, a small data set by hand. This can actually be discrete or continuous. We can do decimal numbers. Histogram, large data sets, right? Best to do it with some form of technology. And there we go, that's the end of this video. Thank you very much for watching. Hopefully it's been useful. Darren from Maths Guru, please subscribe on YouTube if you can. Again, one click from you, it just lets me know that you're watching, all right? And it means the world to me because, again, very few people watch maths videos. Hopefully I'll see you in another video. If not, please take care and stay safe.